Good morning, everyone. I'm Gustavo Quino. I'm currently a postdoctoral researcher at the University of Oxford in the Engineering Science Department. And this morning, I want to share with you some of the work we developed in the last years together with Francesco De Cola, Vito Tagliarelli, and Nick Petrinich. And it's about a technique that makes use of sound, just in the audible range, to get some useful information about what's going on in the experiments, and in this way to try to understand more about the mechanics of what we are studying. In this case, I will show you a bit of the application that we did for fiber bundles. I will start with a brief motivation. I will explain the work we did initially on granular materials, and then I will focus more on the fibers. I'll show some results and conclusions. So as you know, in experimental mechanics, we normally try to gather as much information as we can, depending on the phenomenon we want to observe. If we want to look at displacements, we would use an extensometer. If we want to look at the distribution of shear stresses, we make use of photoelasticity, and if we want to get a full field measurement of temperatures, we have thermal cameras. In our case, we wanted to take advantage of the fact that when materials break, they normally emit sound. And so the piece of equipment that we would use in order to capture this would be this very highly technological microphone. It's just a normal PC microphone that we wanted to use to get some information about, initially, granular materials. What we did, I designed this micro-tensile, micro-compression rig, and we wanted to look at which kind of information we could extract from hearing the crashing of sand grains. We performed some experiments on single grains, and we managed to capture these burst events. And we did similar things with our assemblies of grains, and we concluded that with this technique we were able to hear the burst events, and also we would be exclusively sensitive to fracture, which was something very important. And if you want to look at more details about that study, you can visit our reference. So the next step was trying to use this technique in a different materials, and we looked at some promising application on fibers, in this case fiber bundles, which is basically a collection of parallel fibers all together, non-twisted. And our objectives were mainly three. We wanted to first, again, detect fracture. Second, to find a strength distribution of the fibers within the bundle. So what does this mean? So let's say if you have a bundle of 100 fibers, even though all of them may have the same diameter, the same length, they not have the same strength. Some of them will be weaker than others. And this is because defects are distributed across the material. And in the end, this fiber bundle will have these single fibers within the bundle will show a statistical distribution of strength. And we wanted to see if we could use this technique to find out this distribution of strengths. And finally, we would try to find out if there were some relevant frequencies when we hearing the sound of fibers being broken. And this would be only within the audible range, which is also a limitation of the microphone we were using. Our test rig was we had our universal testing machine and our specimen, our fiber bundle with threaded end caps in the end. And most importantly, we would have our microphone very close to the specimen we were looking at. The microphone was directly connected to a computer through the audio port, and we were using the software Audacity to capture the sound. It's a normal sound recording software. But because the microphone is connected directly to the sound card of the computer, and it has its own preamplification values for the electrical signals, we couldn't assign units to the sound we were recording. However, for this exercise, that was not that relevant because we only wanted to find this breakage events. Basically, we would identify the breakage of one single fiber by the spikes we were finding in the signal. So how do we do that? How can we associate every spike or shape of the signal with one breakage? Well, in order to do that, we need to look at the envelope of the signal. So this is a part of the envelope of the signal, and we will say that this is something that we, from now on, will call sound measurement event. And this will be a sound measurement event, and this will be the breakage of one single fiber whenever that envelope is above certain threshold. In this case, we use a threshold of 20% of the maximum recorded signal. But, okay, what is this threshold? How can we choose it properly? It needs some calibration. I did some single fiber tests, mainly with two reasons. The first one is to make sure the microphones are set up with gains that allow us to actually record a sound at a reasonable level. And the second one is to properly choose this threshold that I was talking about earlier. So what you see now in the screen is the typical experimental data we would find after running the experiment. We would have data over time. Okay? We will have the force over time, the black line, which we get immediately from our load cell. The red spikes that you see would be, for example, the waveform. And if we analyze that using the threshold I was talking about in the previous slide, we can count every sound measurement event that fits that threshold, all the portions of the waveform that are above the threshold. And we could be counting the number of sound measurement events in a cumulative manner and get the number of broken fibers every time. Okay? And let's imagine now that we are at time t, I, where the fiber number I breaks. We can find out the tensile strength of that fiber because we know that that fiber, at that moment, we have a force that is applied over an area, which is equal to the area of every fiber times the number of surviving fibers. And we know the cumulative, so basically we would have the total number of fibers minus that cumulative. But certain rescaling we had to do because this final number of counts was not matching the actual number of fibers within the bundle. And well, but in any case, this would be the distribution of tensile strengths within the bundle in this rescaled manner, and that we called our distribution of apparent strengths. So if we remember the objectives, the second objective was to generate this strength distribution, right? Which we get with the last expression I showed in the previous slide. But now we will compare it also against some distribution that is already quite popularly used when studying fiber bundles, which is the Weibull distribution. And here in the picture you can see Mr. Weibull. There are ways to find the parameters of the Weibull distribution. One of them was given by Yuan Ming and co-authors, and it's based mainly on looking at the maximum stress and the strain at that maximum stress during a test of a fiber bundle. So we will use this to generate, again, a Weibull distribution in this case of values of strength, and we will compare that with those that we obtained with sound measurements. And in order to do that, I made a MATLAB script that runs an analytical model of parallel fibers, non-interacting parallel fibers. And if you want to look at this model, I think I put the Weibull case in my GitHub page. You can play around with it. But what I was doing was initially generating first a Weibull distribution for all the fibers, and in parallel I would generate I would assign to the fibers those strengths that I found using the sound measurement technique, and then I will pull them in strain steps, and whenever the stress in a single fiber would reach its strength, then the module would go to 0, so it stops contributing to the load carrying capacity. So, well, in the time domain, we found indeed these spikes. We identified the sound measurement events, and just as a sample, you can see 4 of these measurement events that I chose. When running the virtual experiment, we can see that in the blue curve we have the experimental, the red one is the result of the virtual experiment using those strengths obtained by our method, by the sound measurement method. And in green you have what it would look like if you use a Weibull distribution, which is much smoother, but lacks of these kind of realistic features of ups and downs caused by several defects in the experiment. And you can see that the error also is less using those strengths from the sound measurement method. Looking at the frequencies with care, actually, we found some main frequencies are in the order of 1.2, 1.5 kilohertz. But these results should be taken with care, because these main frequencies could be not necessarily intrinsically related to the fraction of the fibers, but could be the result of the system fibers plus testing rig. Well, the conclusions I've mainly discussed already. I presented this non-destructive technique. I presented some results with sand grains, with fibers, in which case we proved that it's very useful to detect the initiation and the progression of failure. And most importantly, that it can be implemented with low cost, and it's very easy to implement too. We will continue doing more work with bundles with less number of fibers, and possibly trying to apply to